So very good morning. So welcome back. In fact, it has been more than a week since we posted module 1 of fluid pressure and its measurement. So due to incessant rain and holidays due to the Bengal cyclone, I could not meet you in the last week. So let me summarize what we discussed in module 1 of this particular chapter, fluid pressure and its measurement. So we defined what pressure is, and say for a fluid at rest, the only force it sustains is the only force which is acting on the fluid is the fluid pressure, in addition to the self weight of the fluid. And it cannot sustain any shear force because the fluid is not moving. So there is no tangential force involved, and therefore the fluid pressure always acts in a direction normal or perpendicular to the surface with which it comes in contact. And we derived the expression for fluid pressure, and we proved that by taking an elementary fluid element, a rectangular parallelepiped. We proved that the fluid pressure does not vary in x direction, it does not vary in y direction, that is it remains the same in the horizontal plane, and it varies only in the vertical plane, and again it varies only with the z direction. And we derived dP over dz equal to minus gamma, that is the pressure intensity decreased with increase in elevation z at a constant rate equal to specific weight of the fluid. And we then gave an expression for P in terms of the depth of the liquid, as P is equal to gamma h, where gamma h is the depth of the point at which the pressure is required below the free surface of liquid. So gamma is a specific weight, so P is equal to gamma h we derived, and we defined what a pressure head is, and we worked out a few, of course. Let us continue further on that. Today in this module we will be discussing on Pascal's law. So this is again another fundamental physical law which many of you might be knowing. Still then, as this is an important law which is required to understand the behavior of fluid at rest, the pressure at any point in a fluid at rest has the same magnitude in all directions. The pressure at any point in a fluid at rest has the same magnitude in all directions. So in other words, when a certain pressure is applied at any point in a fluid at rest, the pressure is equally transmitted in all directions and to every other point in the fluid. Now this has to be proved. So what the Pascal's law states, it's a very simple statement. The pressure at any point in a fluid at rest has the same magnitude in all directions. So let us prove this statement of Pascal's law. So we consider a wedge shaped fluid element. So again let me recollect, as we discussed previously in the previous derivation, the x direction is say horizontal, this is positive x direction, suppose this is the origin, and this will be the negative x direction, and xy plane is a horizontal plane, so y will be, this is positive direction of y and this is negative direction of y, and these two axes are mutually perpendicular everywhere. And the third direction, that is z direction, is vertically upward, that is positive z direction. The negative z direction is vertically downward, z negative. So again z is mutually perpendicular to x as well as y. So the same convention we are using. So xy is the horizontal plane, xoy is the horizontal plane, and z is the vertical direction. So we are considering here, instead of a rectangular parallelepiped as we considered in the derivation for and in which we proved that the pressure acts always in a direction normal to the surface with which it comes in contact, and we also proved that P is equal to gamma h. So here we are taking a triangular shaped fluid element, say a triangular prism of that sort. So the dimensions, so infinitesimal wedge shaped fluid element at rest. So the element is arbitrarily chosen within the fluid mass. So dimensions along x direction, it has got dimension delta x. Along y direction, the dimension is delta y. And along z direction, the dimension is delta ez. And we have got an inclined surface. The length of the wedge along the inclined surface is delta s. Inclined plane, the length is delta s as shown, delta s. So delta x along x direction, delta y along y direction, delta z along the vertical direction, and delta s along the inclined plane, the length along the inclined plane. So it is something like a triangular prism wherein you have got a right angle triangle of dimensions, length delta x and height delta z, and the hypotenuse, that is AE or BF, is delta s, and the length of the prism, that is perpendicular to the XOY plane, that is along y direction, is delta y. So it is at rest, the fluid is at rest, and we have already proved that it cannot sustain any shear force, because the fluid is at rest and there is no tangential force involved. The only forces acting on the fluid element are the normal pressure forces exerted by the surrounding fluid on the plane surface of the fluid element and the weight of the fluid element. So the only forces acting on the fluid element that we are considering are the normal, that is perpendicular pressure forces exerted by the surrounding fluid on the plane surfaces of the fluid element. Because if you take this wedge shaped fluid element, how many phases it has got? It has got 4 phases, that is 2 triangular phases. The triangular phases are ADE, the right angle triangle ADE, then BCF. These are triangular phases. Of the element, wedge shaped element, and then the phase of the prism along YZ plane, that is ADCB, this one, ADCB, this one, and then the phase along the inclined plane, that is AEFB, that is along the length delta s, that is the dimensions of the inclined phase AEFB will be delta s by delta y, whereas ADE and BCF, these are triangular phases. So if you want the area, there will be half into delta x, that is the length DE, multiplied by delta EZ, that is the length AD. And then if you want the rectangular face along the plane YZ, that is ABCD, ADCB, the area will be delta Y, delta EZ, that is the area. So 2 triangular phases ADE and BCF, then a rectangular phase ADCB of area delta Y, delta EZ, then inclined plane along the length delta S, of area delta S by delta Y, delta S by delta Y, that is AEFB. So 4 phases it has got. So the only forces acting on the fluid element are the normal pressure forces. So on these planes, the fluid element surrounding this element or the fluid surrounding this element will be exerting a pressure normal to the phase. And you will have the weight of the fluid element which is under consideration. And again, as the fluid element is at rest, it is in static equilibrium. The sum of force components on the fluid element in any direction must be equal to 0. Suppose say x direction, it will be sigma fx equal to 0. Sigma fy equal to 0. In any direction, sigma f is equal to 0. Any direction must be equal to 0. The algebraic sum of force components in x direction is equal to 0, that is sigma fx equal to 0. So fx, how many forces are there in x direction? The pressure force acting along x direction, normal or perpendicular to the left face, that is A DCB, that is along the YZ plane. So what is the area we know? That is delta Y delta Z. So Px into delta Y delta Z. Px is the pressure intensity acting on the left face ABCD, ADCB or ABCD, whatever it is, both are same. So average pressure intensity acting in x direction normal to the phase ABCD. Delta Y delta Z is the area of phase ABCD. Delta Y and then delta Z. That is the area. So Px delta Y delta Z, it is the pressure force acting normal to the phase ABCD of the fluid element in x direction, in positive x direction, that is towards right. Then the other force which is acting in along x axis, that is in the negative x direction, that is on the phase. Suppose if you take the inclined phase, that is ABFE or AEFB. Now the pressure force, because of the surrounding fluid, the pressure intensity will be acting normal to the face, that is at 90 degrees to the face ABFE. That is PS. So let PS. So what is PS? PS is the average pressure intensity acting normal to the inclined phase ABFE. ABFE, this phase. So it is acting normal. That is, say this is the phase, it is acting normal to the phase. This the inclined phase ABFE, it is acting normal to the phase. This is PS, the intensity is PS, average pressure intensity. Now the angle, this angle is alpha, is the angle of inclination of the inclined phase with the horizontal. Therefore, this angle will be, that is the angle between the direction of the pressure intensity PS acting normal to the inclined phase ABFE and the vertical direction, that is Z, along Z axis, that angle will be alpha. So what is the component along x direction? So this is alpha. So this will be 90 minus alpha. So PS cos 90 minus alpha or PS sin alpha is the intensity of pressure in x direction. It is along x axis. In fact, it is negative x direction. So PS sin alpha is the component of pressure intensity PS in negative x direction because it is acting in this direction. This one. This is acting in this direction. So PS sin alpha is the component of PS along the negative x direction. What is the area on which it is acting? This is the area of the inclined phase ABFE. So AB, the length is delta Y, BF it is delta S. Therefore, delta S delta Y is the area of phase ABFE. So what is the pressure force What is the magnitude of the pressure force? Pressure intensity multiplied by area. So pressure intensity is Newton per meter square. Newton per meter square. Area is meter square, so you get the pressure force. So the unit of this quantity is Newton. This is meter square. This is Newton. Newton per meter square. So sigma Fx equal to 0. So Px delta y delta Z, that is a pressure force acting normal to the left face along x direction, and Ps sin alpha delta S delta y is the pressure force acting along negative x direction. That is why I am using minus. So algebraic sum, if it is x direction, positive x direction plus, this is positive x direction plus, this is negative x direction, therefore minus. So the algebraic sum is equal to 0. So the sign convention adopted same as in the previous derivation we had in module 1. The force acting rightward, that is left to right in x direction, is taken as positive, and force acting leftward, that is right to left in negative x direction, is taken as negative force. Then from right angle triangular phase ADE, there is ADE, right, ADE. This is ADE. This is delta x, this is delta x, this is delta Z. So what is sin alpha from this? Sin alpha will be opposite by adjacent, opposite by hypotenuse. Opposite is AD divided by hypotenuse is AE. What is AD? AD is delta Z. AE is delta S. Therefore, delta S is equal to delta Z by sin alpha. Delta S is equal to delta S is equal to delta Z by sin alpha. That's what. So from the right angle triangular phase ADE of the fluid element, so we have sin alpha is equal to AD by AE, that is delta Z by delta S, therefore delta S is equal to delta Z by sin alpha. So substituting delta Z by sin alpha in this equation, that is in this equation, we have Px delta y delta Z minus Ps sin alpha into delta Z by sin alpha delta y. So if you prove it, ultimately you get Px is equal to Px. So what is the meaning? The pressure intensity in x direction is equal to the pressure intensity in s direction. What is s direction? Normal to the inclined face of the wedge shaped fluid element. Similarly, let us consider the z direction. So the algebraic sum of force components in z direction is equal to 0, that is sigma f is equal to 0. So again we will go back to the diagram. So in z direction how many forces are acting? So z direction you have 3 forces. One is the component of Ps, acting in the vertical downward direction or acting normal to the inclined face ABFE. Okay. That is this one. So what is the vertical component of Ps? That is Ps cos alpha. Ps cos alpha. So Ps cos alpha is the vertical component of the pressure intensity Ps. Ps acts normal to the inclined face ABFE. If you multiply by the phase, the area of the phase ABFE, the inclined phase delta S delta y, you get the magnitude of the pressure force acting on the inclined face in the vertical downward direction, that is okay. So this is vertical downward, therefore this will be minus, this is a negative quantity. And there is another force acting on the bottom face of the wedge shaped element. What is the bottom face? Bottom face is CDEF. CDEF. This one. CDEF. That is along the XY plane. So, what is the area? Delta X by delta Y is the area. What is the pressure intensity? The pressure intensity acting vertically upward, normal to the face, bottom face of the wedge shaped element, that is PZ. PZ is the pressure intensity. So, PZ multiplied by delta X delta Y is the area of the bottom face. So, PZ delta X delta Y, that is acting in the vertical upward direction, therefore positive, that is positive is the direction. Then minus PS cos alpha delta S delta Y, that is acting vertically downward on the inclined face, minus you have the self weight of the fluid element. So, what is the self weight of the fluid element? That is specific weight multiplied by volume of the fluid element. Volume of the fluid element. Volume of the fluid element. How will you find out the volume? It is a wedge shaped element. So, area of the triangular face multiplied by the length of the prism, that is half into delta X delta Z multiplied by delta Y. Half into delta X delta Z is the area of the triangular face multiplied by the length of the prism, that is delta X Y, sorry, delta Y. Delta Y. Delta Y. So, half multiplied by delta X delta Z is the area of the triangular face of the element. Half multiplied by delta X by delta Z multiplied by the length of the prism, that is delta Y, right, this one, that is AB, that will be delta Y. So, this is the volume multiplied by gamma. So, gamma multiplied by volume of the fluid element, that is equal to 0. Why this is minus? Because this is also acting in the vertical downward direction, that is negative Z direction. So, again I summarize, PZ is the average pressure intensity acting in Z direction normal to the bottom face CDEF of the element. Delta X delta Y is the area of the bottom face. So, PZ delta X delta Y gives the pressure force acting normal to the face CDEF of the element. This one is acting vertically upward. Then PS is the average pressure intensity acting normal to the inclined face. PS cos alpha is the component of pressure intensity PS, its P suffix S, in vertical downward direction, that is negative is the direction acting on face ABFE, that is the inclined face. Delta S delta Y is the area of the inclined face ABFE. So, PS cos alpha delta S delta Y gives you the pressure force component in the negative is the direction, that is vertical downward acting on the inclined face ABFE. This one. Then the weight of the fluid element, that is self weight of the fluid element. So, again the sign convention I repeat, the same as we adopted in the previous derivation. The force acting vertically upward in Z direction is taken as positive force, and the force acting vertically downward in negative Z direction is taken as negative force. So, again from right angle triangular face the ADE of the fluid element, you can write that delta S is equal to delta X by cos alpha. So, substituting delta S is equal to delta X by cos alpha in this equation we have already written. This becomes ultimately that PZ equal to PS. So, what we proved earlier, we proved that PX is equal to PS, and now we have proved PZ equal to PS. That is, the pressure intensity on the fluid element in x direction is equal to the pressure intensity on the fluid element in the, that is normal to the inclined phase, that is in S direction. Similarly, the pressure intensity in Z direction is equal to the pressure intensity in S direction, that is normal to the inclined phase of the fluid element. So, we have Px is equal to Pz equal to Ps. So, this equation proves that the pressure intensity exerted on the fluid element is the same in all directions, all directions. So, hence the Pascal's law is proved. Now, let us derive the relationship between atmospheric pressure, absolute pressure and gauge and vacuum pressures. Relationship between atmospheric pressure, absolute pressure and gauge and vacuum pressures. So, we are talking about 4 pressure terminologies: atmospheric pressure, absolute pressure, gauge pressure and then vacuum pressures. Vacuum, please take note of the spelling, it is VACUUM. Atmospheric pressure. So, what is atmospheric pressure? It is a normal pressure, that is exerted by atmospheric air on surfaces with which it comes in contact. Say we talked about free surface of liquid. So, what is free surface? So, where the atmospheric pressure acts, say for example, you take a container, open at the top, which is storing a liquid which has got a free surface. This is the free surface. And here on the free surface, what acts? The atmospheric pressure acts. In what direction? It is acting perpendicular to the free surface. The pressure exerted by atmospheric air on the surface of the liquid with which it comes in contact is the atmospheric pressure. Now, the magnitude of atmospheric pressure varies with altitude. So, how it is measured? Atmospheric pressure can be measured using a barometer. So, that is why atmospheric pressure is also called as barometric pressure. At sea level, that is at sea level, under normal conditions, under standard conditions of temperature and pressure, the equivalent values of the atmospheric pressure are, it is in fact, this should be 10.1043 into 10 power 4 Newton per meter square. Please make note of, it is not 104, it is 10 power 4 Newton per meter square, or it is 1.03 kgf per centimeter square. So, 10.1043 into 10 power 4 Newton per meter square, or 1.03 kgf per centimeter square, or you can also put it in terms of equivalent column of a liquid as 10.3 meters of water or 760 millimeters of mercury. So, at sea level under normal conditions, the equivalent values of the atmospheric pressure expressed as an intensity in SI system or the CGS system, it is kilogram force per centimeter square, or MKS system, and 10.3 meters of water as a pressure head in terms of equivalent column of water or in terms of equivalent column of mercury as 760 millimeters of mercury. So, generally the fluid pressure at a point can be measured with respect to 2 most common datum. So, what are these 2 datum? Absolute zero pressure and then local atmospheric pressure. So, we can express the fluid pressure at a point with respect to 2 different datum. You can take either absolute zero pressure as the datum. So, absolute zero pressure is the pressure corresponding to complete vacuum. What is absolute zero pressure? Pressure corresponding to complete vacuum. So, this is the bare minimum pressure that can prevail at any point. local atmospheric pressure. So you can either code the pressure with respect to local atmospheric pressure. That is, you can treat the atmospheric pressure as 0. That is convenient. So normally you can code the pressure at a point whether it is below atmospheric or above atmospheric. Okay. So absolute zero pressure, that is what I mentioned earlier. It is the minimum pressure, bare minimum, that can prevail at a point under natural or forced conditions. It is the zero pressure prevailing under complete vacuum. Then absolute pressure. What is absolute pressure? Absolute pressure, when pressure at a point is measured with respect to absolute zero or complete vacuum as the datum. So this is the datum. So absolute zero or absolute vacuum is considered as the datum. It is called absolute pressure. What is gauge pressure? When pressure at a point is measured with respect to the local atmospheric pressure, this is the datum. Local atmospheric pressure is the datum. It is called gauge pressure. The gauge pressure, because it is what all pressure gauges are calibrated, right, to measure, right. Say the pressure gauges read 0 normally when exposed to atmosphere. So the pressure gauges are calibrated such that they read only the difference between the pressure of fluid to which they are connected and the atmospheric pressure. So the pressure gauges are calibrated in such a way that they read only the pressure difference between the pressure of the fluid to which they are connected and the atmospheric pressure, only the difference they measure. So atmospheric pressure is read as 0 by these pressure gauges. They are calibrated in such a fashion. And that is why the gauges measured by pressure gauges are called a gauge pressure. And again, the gauge pressure can be positive or it can be negative. If the pressure of the fluid is below atmospheric pressure, then that difference, that is the difference between the reading as shown by the pressure gauge and the atmospheric pressure, that is called vacuum pressure or suction pressure or negative gauge pressure. So there are 3 different names, synonyms: vacuum pressure, suction pressure or negative gauge pressure. So if the pressure of the fluid is below atmospheric pressure, it is designated as vacuum pressure or suction pressure or negative gauge pressure. So what is this? It is the value or is the amount by which it is below atmospheric pressure. So vacuum pressure is the amount by which it is below atmospheric pressure. So a pressure gauge intended to measure vacuum pressure is called a vacuum gauge. What does a vacuum gauge means? It means it measures pressure of the fluid below atmospheric pressure. How much? All values of absolute pressure are positive, since in case of fluids the lowest absolute pressure that can possibly exist corresponds to absolute zero or complete vacuum. So if you are taking absolute zero as the datum or complete vacuum as the datum, then absolute pressure at any point will always be positive, because the bare minimum pressure that you can measure at a point is only absolute zero or complete vacuum. So gauge pressures are positive if they are above atmospheric pressure, and they are negative if they are below atmospheric pressure. So now all these points which we discussed can be shown in the form of a diagram, figure. The relationship between absolute atmospheric gauge and gauge negative pressures can be shown by this diagram. See, I have referred the 2 datums. This is one datum, that is this one, that is the absolute zero pressure or complete vacuum. This is one datum. This is one datum. The other datum is this one, that is the atmospheric pressure or gauge zero, that is another datum. So you can code the pressure at a point either taking the atmospheric zero pressure or complete vacuum as the datum, or atmospheric pressure or gauge zero as the datum. Atmospheric pressure or gauge zero. As I told, any pressure gauge, when it is idle, it will indicate zero value, that is, it will take the atmospheric pressure as zero. So what is indicated by the needle of a pressure gauge is only the difference between the pressure of the fluid with which it is in contact and the atmospheric pressure. So let us consider 2 points, A and B. This is, say, point A, another point B. Points A and B. A is above atmospheric, B is below atmospheric. This is the atmospheric pressure. This is the local atmospheric pressure. The atmospheric pressure varies with place, varies with altitude, varies from time to time. So, of course, slightly. It varies with temperature. It varies with altitude. So, the local atmospheric pressure, let it be P atmospheric. So, I am considering a point A wherein the pressure is above atmospheric. Okay. The pressure at A is gauge positive and the pressure at B is gauge negative. So, B is a point where it is below atmospheric. So, here it is gauge negative. So, what is absolute pressure at A? Absolute pressure at A will be atmospheric pressure plus this one. What is this? It is the gauge pressure at A. Similarly, if you take the point B wherein the pressure is below atmospheric, so pressure at B will be atmospheric pressure minus vacuum pressure. So, P atmospheric minus vacuum pressure at B. So, absolute pressure at A is atmospheric pressure plus gauge pressure at A. Absolute pressure at B is equal to atmospheric pressure minus vacuum pressure at B. So, absolute pressure at A will be atmospheric pressure plus gauge pressure at A. Absolute pressure at B will be atmospheric pressure minus vacuum pressure at B. So, in general you can combine these two things and give the relationship between the various pressures as a single equation which is applicable for any point, whether there the pressure is below atmospheric or above atmospheric. So, absolute pressure at any point will be atmospheric pressure plus or minus gauge pressure. So, when you use plus, when the pressure at the point is above atmospheric. When you will use minus, when the pressure at the point is below atmospheric. So, the gauge pressure may be positive or negative depending on whether the pressure at the point is above atmospheric or below atmospheric. So, I hope you have understood. So, we stated the Pascal's law, derived the Pascal's law, or proved that the pressure intensity is same in all directions, and we derived the relationship between atmospheric, absolute and gauge pressures. The gauge pressure can be positive or negative depending on whether the pressure at the point to be measured is above atmospheric or below atmospheric, and in expressing the pressure at a point we can use two datums, that is complete vacuum or absolute zero or atmospheric pressure. So, when we are using atmospheric pressure as the datum, atmospheric pressure is treated as zero even though it has got a value. The atmospheric pressure varies with altitude, varies with temperature. Now, let us work out some basic examples to understand the underlying concept of pressure. So, example 1, express a pressure intensity of 5 kgf per centimeter square in all possible units. Take the barometric reading as 76 centimeters of mercury. So, pressure intensity, when I say pressure intensity, it means in excess of atmospheric pressure. When I say simply pressure or pressure intensity, it means the pressure in excess or of atmospheric pressure. Suppose say that it is say 5 kgf per centimeter square. So, barometer reading gives what? The atmospheric pressure in equivalent column of mercury, it is given, that is 76 centimeters. So, let us express the given pressure intensity in all possible units, that is as intensity as column of say water. So, first in gauge units. So, what is pressure intensity? So, I am converting kilogram force per centimeter square to Newton per meter square. So, 1 kilogram force is 9.81 Newton. So, 5 multiplied by 9.81 to get in newtons, and centimeter square will be 10 power minus 4 meter square. So, that will be 490,500 Newton per meter square. So, that is if you convert it to kilonewtons, you divide by 1000, so 490.5 kilonewton per meter square. So, we expressed the pressure intensity which is given in kilogram force per centimeter square in Newton per meter square, that is in SI system. So let us put the pressure intensity in equivalent column of water. What is P is equal to? We have P is equal to gamma H. That is saying gamma W HW. What is gamma W? Specific weight of water, that is 9810 Newton per meter cube. What is P? The pressure that we have just determined, that is 490500 Newton per meter square. So P is 490500 Newton per meter square. So I want the equivalent column of water which is required to exert this amount of pressure. So HW is equal to P by gamma W. So that is 490500 Newton per meter square divided by 9810 Newton per meter cube. So you get 50 meters of water. So the equivalent column of water that is required to exert a pressure of 490500 Newton per meter square is 50 meters of water. So then pressure intensity in equivalent column of mercury, to exert the same amount of pressure. So in that case we use P is same, it is gamma m into Hm. What is gamma m? Specific weight of mercury. What is specific weight of mercury? Specific gravity of mercury multiplied by specific weight of water. That's 13.6 multiplied by 9810 Newton per meter cube. That is 133416 Newton per meter cube. So Hm will be pressure intensity divided by specific weight of mercury. You get 3.677 meters of mercury. That is in gauge units. Then in absolute units, that is taking absolute zero as the datum. So absolute pressure is what? Atmospheric pressure plus gauge pressure. Now let us determine the intensity of atmospheric pressure, because atmospheric pressure is given in equivalent column of mercury as 76 centimeters, that is 0.76 meter. So what is atmospheric pressure? Atmospheric pressure is equal to specific weight of mercury into equivalent column of mercury to exert this atmospheric pressure. So this will be 133416 Newton per meter square multiplied by 0.76 meter of mercury. You get 101,396.2 Newton per meter square as the atmospheric pressure. So gauge pressure we have just determined, it is 490,500 Newton per meter square. So absolute pressure will be atmospheric pressure plus gauge pressure. So you get this much. Similarly, you can find out an equivalent column of water. Equivalent column of water in absolute units. In absolute units, using this expression. P atmospheric is equal to specific weight of mercury multiplied by equivalent column of mercury, that is equal to specific weight of water multiplied by equivalent column of water. So you can find out the absolute pressure in equivalent column of water will be 60.336 meters of water, that is in absolute units. In absolute units. Okay. In equivalent column of mercury, using the same concept, absolute pressure head in meters of mercury will be, this is the atmospheric pressure in equivalent column of mercury, that is 0.76 meter, plus the column that is required to exert a pressure of 5 kgf per centimeter square, that is 3.6765 meters of mercury. So you get in absolute pressure head in meters of mercury will be 4.4365 meters of mercury. This is another example. Find the depth of a point below free surface in a tank containing oil where the pressure intensity is. So you are asked to find out the depth of a point which is below free surface in a tank containing oil where the pressure intensity is. Say let the point A has a pressure intensity of this much given. You are asked to find out what is the depth at which the point A is located in the tank which is containing oil of specific gravity 0.9. So you use P is equal to gamma H, that's all. What is P? P is the pressure intensity, that is 9 kgf per centimeter square. Put it in Newton per meter square. So 9 multiplied by 9.81 Newton into 10 power 4 meter square, that will be 882900 Newton per meter square. Then what is gamma? Gamma is the specific weight of oil, that will be 0.9 into 9810 Newton per meter cube, using the concept of specific gravity. So, specific gravity of oil is equal to gamma oil divided by gamma water. So, specific gravity of oil is 0.9, gamma oil is that what we want, gamma water is 9810 Newton per meter cube. So, you get gamma oil, that will be 0.9 into 9810 Newton per meter cube. So, H will be P by gamma, P by gamma. H is what is required, P is this much, 882900 Newton per meter square. Divided by specific weight of oil will be 8829 Newton per meter cube. So, you get 100 meters, 100 meters. So, this will be 100 meters. So, the last problem for this session, convert a pressure head of 15 meters of water to meters of oil of specific gravity 0.75 and meters of mercury of specific gravity 13.6. So, we know that P, we have already discussed in module 1 as P is equal to gamma 1 H1, sorry, equal to gamma 2 H2. That is, to exert a pressure intensity of P Newton per meter square by two different liquids of different specific weights, gamma 1 and gamma 2, what is the depth of liquids required? So, that is the concept. So, I have say HW equal to 15 meters of, that is water. I have to convert this to meters of oil as specific gravity. So, we can also use say P is equal to S1 into gamma W into H1 is equal to S2 into gamma W into H2. So, you can also write like this, you can also S1 H1 equal to S2 H2. So, we have this one, because gamma W and gamma W can be cancelled. So, S1 H1 equal to S2 H2. Please note, S1 H1 is not equal to P or S2 H2 is not equal to P. This is only when you operate with a specific gravity and the head, you can use this equation. So, this the product of S1 and H1, specific gravity and head of liquid, will not give the pressure intensity, should not. So, I have say SW HW equal to S oil into H oil. So, what is SW? It is 1, specific gravity of water is 1. What is head of water? 15 meters. Specific gravity of oil is 0.75, 0.75 multiplied by H oil. So, you can get H oil. H oil is equal to 1 multiplied by 15 divided by 0.75. So, instead of specific gravity, I am using the specific weight, that is all. So, it is gamma W HW divided by gamma oil. So, you get 20 meters of oil. Similarly, to find the equivalent column of mercury of specific gravity 13.6, equivalent to pressure head of 15 meters of water can be derived using this expression. P is equal to gamma W HW equal to gamma IM HM, the same pressure intensity. So, specific weight of water is 9810 Newton per meter cube. Equivalent column of water in meters to exert the pressure intensity of P, that is 15 meters here. specific weight of mercury, it is 13.6 specific gravity of mercury multiplied by specific weight of water. So, you get 133,416 Newton per meter cube. I want the equivalent column of mercury as specific gravity 13.6 to exert the pressure intensity, same pressure intensity P. So, you get HM is equal to 1.1029 meters of mercury. So, with this we come to the conclusion of this module. So, again I summarize, we discussed on Pascal's law, relationship between atmospheric pressure, absolute pressure and gauge pressures. The gauge pressure can be positive or negative depending upon whether the pressure at the point is above atmospheric or below atmospheric. Then we worked out some basic very fundamental problems to understand the concept of pressure. So, thank you very much. Let us meet in module 3, in which we will be talking about the measurement of pressure using manometers. Thank you.